Artificial Intelligence Dr. www.abcpharma.net/English. User question: what are the specific molecular mechanisms underlying the relationship between sleep duration and quality and the risk of developing chronic diseases such as cardiovascular disease, diabetes, and neurodegenerative disorders? Claude AI answer: this question touches on a critical area of sleep research with significant public health implications. The molecular mechanisms linking sleep to chronic diseases are complex and multifaceted. Let's break down the key aspects. 1. Cardiovascular disease. A. Inflammation. Sleep deprivation activates NF-kappa B pathways, increasing production of pro-inflammatory cytokines, Illinois 6, TNF-alpha. Chronic low-grade inflammation contributes to atherosclerosis and endothelial dysfunction. B. Oxidative stress. Inadequate sleep increases reactive oxygen species, ROS, production. Oxidative stress damages vascular endothelium and promotes atherogenesis. C. Sympathetic activation. Sleep loss activates the sympathetic nervous system, increasing catecholamine release. Chronic sympathetic activation leads to hypertension and cardiovascular strain. D. Metabolic dysregulation. Sleep disruption alters leptin and ghrelin levels, affecting appetite regulation. Insulin resistance increases, promoting dyslipidemia and atherosclerosis. E. Coagulation. Sleep deprivation increases platelet activation and fibrinogen levels. These changes promote a prothrombotic state. 2. Diabetes. A. Insulin sensitivity. Sleep loss impairs insulin signaling pathways in skeletal muscle and adipose tissue. Decreased GLUT4 translocation reduces glucose uptake. B. Beta cell function. Chronic sleep deprivation may lead to beta cell dysfunction and reduced insulin secretion. Stress in beta cells contributes to this impairment. C. Adipose tissue. Sleep loss alters adipokine production, e.g., decreased adiponectin, increased resistin. These changes contribute to systemic insulin resistance. D. Hypothalamic pituitary adrenal, HPA, axis. Sleep deprivation activates the HPA axis, increasing cortisol production. Chronic elevation of cortisol promotes insulin resistance and visceral adiposity. E. Circadian misalignment. Disruption of circadian rhythms affects pancreatic clock genes. This misalignment impairs glucose homeostasis and insulin secretion timing. 3. Neurodegenerative disorders. A. Amyloid beta clearance. Sleep promotes clearance of amyloid beta through the glymphatic system. Chronic sleep deprivation leads to amyloid beta accumulation, a hallmark of Alzheimer's disease. B. Tau protein. Poor sleep quality is associated with increased tau protein phosphorylation. Hyperphosphorylated tau contributes to neurofibrillary tangle formation in Alzheimer's and other tauopathies. C. Neuroinflammation. Sleep loss activates microglia and increases neuroinflammatory markers. Chronic neuroinflammation contributes to neurodegeneration. D. Oxidative stress in the brain. Sleep deprivation increases oxidative stress in neurons. Oxidative damage accumulates over time, contributing to neuronal loss. E. Synaptic plasticity. Sleep plays a crucial role in synaptic homeostasis and plasticity. Chronic sleep disruption may impair synaptic function and contribute to cognitive decline. F. Protein aggregation. Sleep promotes the clearance of protein aggregates associated with various neurodegenerative disorders. Chronic sleep disruption may lead to accumulation of alpha-synuclein, Parkinson's, and Huntington's. Common mechanisms across diseases. 1. Epigenetic changes. Sleep deprivation can alter DNA methylation and histone modification patterns. These epigenetic changes affect gene expression in multiple tissues, potentially contributing to disease risk. 2. Circadian rhythm disruption. Sleep disturbances often involve circadian misalignment. Disruption of clock genes, e.g., BMAL1 clock, affects metabolic pathways, inflammatory responses, and cellular repair mechanisms. 3. Cellular senescence. Chronic sleep deprivation may accelerate cellular senescence. Accumulation of senescent cells contributes to age-related diseases and chronic inflammation. 4. Mitochondrial dysfunction. Sleep loss can impair mitochondrial function and dynamics. Mitochondrial dysfunction is a common feature in cardiovascular disease, diabetes, and neurodegeneration. 5. Telomere attrition. Poor sleep quality is associated with accelerated telomere shortening. Telomere attrition is linked to cellular aging and increased disease risk. Understanding these molecular mechanisms is crucial for developing targeted interventions to mitigate the health risks associated with poor sleep. Future research directions may include: 1. Identifying biomarkers of sleep-related health risks for early intervention. 2. Developing pharmacological interventions targeting specific sleep-related molecular pathways. 3. Exploring personalized sleep recommendations based on genetic and epigenetic profiles. 4. Investigating the potential of circadian rhythm-based therapies in disease prevention. 5. Elucidating the interactions between sleep, gut microbiome, and chronic disease risk. In conclusion, the relationship between sleep and chronic disease risk involves a complex interplay of molecular mechanisms. Addressing sleep quality and duration may offer a powerful approach to preventing and managing these conditions, highlighting the importance of sleep as a pillar of public health.